Okay, welcome to part two of our introduction to light. So this time we're going to explore light as a particle. So on a macroscopic level, light certainly looks like a wave. It behaves in many of the same ways a wave would behave, but at the atomic level, it has some very particle-like qualities. One of the biggest pieces of evidence for this is the discrete spectra of atomic gases. So this is a big clue that light acts like a particle, and we call this particle of light a photon. So when you look at atomic gases through a spectrometer or a spectroscope, you don't see a continuous spectrum like a rainbow, like what we would see maybe through a prism, right? If we're just looking at a white light. You see these discrete lines at different wavelengths. And this pattern is different for every atom, right? So we have an unknown gas here, but this is different from helium. This is the spectrum of helium. Again, we have discrete lines. We have oxygen has yet another different spectrum, neon, argon, xenon. They have different, basically, yeah, different fingerprints. So what does this mean for light? Okay, so atoms consist of a nucleus with at least one proton and most of the time some neutrons as well, though not all the time. And this nucleus is orbited by what we call an electron cloud. So orbits correspond to the energy of the electrons. Electrons can be excited into higher orbits. Higher orbits require higher energy, but those electrons really like to be in a lower energy state, a lower energy level if possible. So they quickly will decay by emitting a photon that is the energy difference between levels. And these are discrete, like rungs on a ladder, right? You can go up or down one or two steps, but you can't go a half step. So the this a picture right here kind of shows like an electron in this higher energy level. It wants to decay down to this energy level, and it will emit the exact difference in energy from this level to this level. Okay, atoms, just for reference, are really mostly empty space. If we put a grape seed in the middle of a football field, that would represent the nucleus. The electron cloud would be about 5 football fields out from there. So really, when we say that atoms are mostly empty space, right, like we mean it, right? There's not a lot there. So different atoms, though, have different sized nuclei with different patterns of electrons. So different atoms have different electron orbits. So when you excite the electrons, it will give off photons of different energies. The energy of the photons is quantized, which means it has a very specific value. Only certain energies of light can excite or be emitted by an atom. And this is kind of how we illustrate like these energy levels. We have excited states and a ground state. And here we have energy levels of hydrogen. We have the ground state, and then it takes an energy to get up to the second energy level, and then more and more and more as you go up. So we can use the different patterns to our advantage because these spectral lines act as fingerprints of the source, right? You can get spectral lines from emission or when excited gas gives off photons, or from absorption when colder gas absorbs some background light. So we have here a demonstration of a continuous spectrum. It's basically a rainbow that white light is composed of, right? It has some of each color. An emission spectrum, so these are emission lines. We see bright lines appear through a spectrograph against a dark background. And then absorption lines are kind of the inverse of that, right? Dark lines appear against a continuous spectrum. These dark lines indicate where light and energy is being absorbed. One of the early important discoveries of the nature of photons was by Albert Einstein in 1905 when he described the photoelectric effect. He demonstrated that photons can cause a current. They can cause electrons to move in a metal. So basically, kind of, he shined light on a metal and realized that this can cause a current. Not only did he realize that, but photons of different colors, right, of different frequencies, cause a different energy or a different voltage. So he showed that the energy was related to the color and that light can behave like a particle. So the big takeaway is that energy of photons depends on the frequency or equivalently the color, right? Um, you can find the energy really by using this. It's a very simple, a simple equation where E is the energy of the photon, F is the frequency, and H is a constant called Planck's constant. And what we find when we actually look at this is that UV or blue light has a larger frequency and they have a higher energy. Radio, infrared, and red light, they have lower frequencies, so they have lower energy. So we asked at the beginning of part one, like really what is light? Like what's its source? Like is it a wave like we talked about in the last lecture, or is it a particle? Maybe it's both, or maybe it's neither, right? So this kind of ambiguity is called wave-particle duality. Light has properties of both particles and waves. It can be a little bit hard to kind of wrap your mind around, but this is really what the evidence shows us. So if you haven't already, please watch Dr. Hassel's demo videos. And if you have any questions about this, just shoot me an email or come by during my office hours.